This is the Vertical Vanguard project, redefining fixed-wing VTOL UAV design. My name is Alec Delgado.
Mercedes Flores,
Matthew Villanueva,
and Seth Rodriguez.
The fixed-wing configuration for a UAV uses rigid wings and a horizontal takeoff propulsive system as seen on the left. This configuration has good aerodynamic performance, making it the preferred choice for missions with long range and endurance. This comes at the cost of requiring a runway for takeoff when it may not always be accessible to provide. The VTOL configuration features 4 motors, as seen on the right, to give the UAV the capability to vertically take off and land, similar to commercial drones. This is advantageous in environments where runways may not always be accessible. A major disadvantage of this configuration is its relatively poor aerodynamic performance, enabling it for use with shorter mission durations and ranges.
The objective of the Vertical Vanguard project is to design and analyze a fixed-wing VTOL UAV hybrid that combines the advantages of both configurations. The design would be based on existing theoretical designs seeking to achieve a similar performance. The simulated results from the theoretical design would be compared with actual results from the Vertical Vanguard project, validating its performance.
The motivation and relevance of this project is to expand accessibility in educational, research, and commercial applications, as well as to achieve comparable aerodynamic efficiency from methodology to experimental.
Key outcomes of the project include the validation of the UAV's performance and functionality, coming up with an optimized design that prioritizes both the VTOL functionality and aerodynamic performance of fixed-wing aircraft, and to deliver a cost-effective solution.
The existing literature that we analyzed was from the University of Iowa. The study follows a structured methodology to design and analyze a fixed-wing VTOL UAV. The design requirements and objectives were based on a set of operational goals that would be theoretical for this VTOL UAV to function. The report demonstrates the step-by-step process in designing a VTOL UAV that the Vertical Vanguard project team referenced to create a physical model. The actual results from the physical model were then compared to the theoretical results from the literature.
On the left is our initial design concept as a CAD model, created during the early design phase to visualize the geometry, estimate performance, and plan for fabrication. On the right is our final physical prototype. It includes an updated design with component integration and material adjustments for real-world testing and fabrication constraints.
This is a simulation of the NACA 4412 airfoil done on XFLR5. This is one of the airfoil candidates we investigated prior to finalizing our design. The simulation was ran at an airspeed of 12 meters per second, and it shows the lift and drag distribution over the wing for varying angles of attack.
The front wing and the back tail use the same airfoil characteristics. We performed a digitized manual tracing method of the airfoil using a software called WebPlot Digitizer. This software was used to extract these coordinates and then make a comparison similarity to the Phoenix 2400 airfoil.
The airfoil geometries from considered airfoils were imported into XFLR5 to analyze the lift-to-drag ratio over various angles of attack. The analysis was conducted on the 2D shapes of each airfoil from an angle of attack of -10 to 6 degrees in 2-degree increments. The selected Reynolds number was 200,000, a number chosen based on prior analyses of similar scale and requirements. As previously mentioned, the geometry of the selected airfoil was extracted and comparable to that of the Phoenix 2400 airfoil, whose analysis is depicted by the dashed line. From this graph, it was concluded that the selected airfoil provided a good enough lift-to-drag ratio relative to the other considered geometries. This made it an ideal candidate, especially since it simplified the manufacturing process of the project.
This graph shows part of theoretical data analysis for our chosen foam glider, the saw speed versus the weight. At 150 grams, the saw speed is 7.85 meters per second. At 200 grams, the stall speed is 9.06 meters per second. And at 300 grams, the stall speed is 10.13 meters per second. The stall speed versus weight shows the heavier weight need higher speed to stay aloft. A lift-to-drag ratio of 6 led to a glide distance of 26.98 meters. A ratio of 8 leads to a distance of 35.98 meters, and a ratio of 10 leads to the glide distance of 44.97 meters. The glide distance versus lift-drag ratio demonstrates how aerodynamic efficiency boosts flight range. This graph demonstrates the comparison of lift and drag forces as airspeed increases. Lift grows faster due to higher lift coefficient, enabling flight while drag also rises.
Our original design for the VTOL motor mounts are shown on the left side, using a cup design to secure the motors in place. The issue with this design is that it accrues too much heat by enclosing the motors with almost no ventilation. It also splits our wooden rods used to support these motors into two separate pieces, compromising the structural integrity of the VTOL rig. The new updated motor mounts allow one rod to be fed through the motor mount, improving the stability of the rig while also allowing full ventilation.
We used a foam cake glider as the base for our prototype. A hot wire foam cutter was used to cut the fuselage to its desired shape and to manufacture the horizontal stabilizer. The stabilizer is made up of the same wing as the glider, having the same airfoil. Additional material was removed from the fuselage to create space for the electrical components of the flight systems. The VTOL structure was then laid out to measure the desired distance of the horizontal stabilizer. This was the wing that was cut to make the horizontal stabilizer. The masking tape was used as a guide while using the hot wire to make a straight cut.
The flight controller and the electronic speed controller are critical components of our project. The flight controller acts as a brain for our UAV, keeping it stable and uniform while the ESC controls the rotational speed of our motors. These components required a lot of precise soldering, which our team honestly struggled with. Our soldering work and poor wire stripping was believed to be the cause of our ESC board and one of our motors burning out during testing. Thankfully, after gathering new ESC and motors, we were able to successfully connect our system.
The motors that we bought were designed for a small drone. The original wires were not long enough to reach the flight controller and the fuselage from the VTOL structure, requiring us to extend the wires using solder. After frying an ESC and a motor, extra care was taken while soldering to ensure good electrical connections with as little exposed wire as possible to prevent any short circuits.
This is the component layout and structures. Our VTOL motors were screwed into respective motor mounts while the battery, flight controller, ESC, and receiver were secured in a cardboard undercarriage, which we later poked holes through for ventilation. The horizontal motor was secured to the front of the fuselage, equipped with a 10-inch propeller, an ESC, and a battery, with the receiver velcroed on top of the fuselage.
Going into our testing videos. In our first test, the propellers were not fastened on correctly. This caused two of our propellers to fly off high and we lost one of them.
In flight test number 2, we switched our propellers. These new propellers were 6 inches as opposed to 5 inches, which would result in higher thrust. However, all the propellers were designed to spin clockwise when this kind of configuration requires 2 propellers each to spin in opposite directions to prevent unwanted yaw. This resulted in unexpected oscillatory behavior.
We then ordered the correct propellers and installed them before flight test number 3. In flight test 3, the UAV did successfully lift off the ground but then quickly flew to the side. From a visual inspection, the overall structure is very susceptible to twisting, which contributes to stability issues. Additionally, the weather was very windy that day, which contributed to the issues.
In flight test 4, it is evident that the structure lacks rigidity as seen by the excessive vibrations.
Wooden spars were added to the wings to improve the rigidity for future tests.
We review the bill of materials for our project. This slide lists the primary components required for our aircraft system. First, we have 2 Lidl glider kits at $38.75 for both. These serve as a base airframe structure for our design. We're using a SpeedyBee F405V4 flight controller to manage flight control and motor commands. That's priced at $79.99. Alongside it, we included an additional SpeedyBee 4-in-1S board for expanded motor control costing $49.99. Our propulsion system includes 4 SpeedyBee 1800 kV motors totaling 4 units at $69.99 each. These provide the necessary thrust needed for vertical flight control. We added a horizontal flight S board for $16.99 to manage the glider's horizontal propulsion. For control, we're using 2 FlySky FS I6RC transmitters and receivers, totaling to $105.98 for both. Finally, we included a 4S LiPo battery from Ovionic at $20.89 to power our system. Moving to the second half of our materials list, we cover additional power and propulsion elements. We've included a 6S LiPo battery from Ovionic at $29.44, supporting high current draw applications. We include the Flash Hobby brushless motor priced at $19.99, which offers redundancy or additional thrust as needed. For safe charging, a LiPo charger HBCRC charger is included at $39.99. We also need multiple propellers, 10 10-inch horizontal propellers at $14.49 each, and 14 6-inch vertical propellers at $11.89 each. each to support VTOL or multi-axis movement. The total cost for all our components across both sides comes to $538.25. This slide highlights what went right and where we ran into complications during the project. On the success side, we got all the motors running, completed Betaflight firmware configuration, and overcame multiple unexpected issues like incompatible parts and a burnt motor. Ultimately, the system was able to generate enough thrust to lift off the ground, which was a success. However, we faced several complications. Initially, we had incorrect and incompatible components, especially with the VTOL flight controller and receiver. Learning to use Betaflight and developing soldering skill cost us significant time. We also experienced hardware failures like an S-board and motor burning out and even overheating. While the vehicle did briefly lift off, it struggled to stay airborne and eventually lost motor control again. Based on those outcomes, here are some proposed improvements for both structure and testing. Structurally, we suggest using glass wings for better rigidity, adding stringers for reinforcement, implementing durable landing gear, making the frame stiffer overall, and finally designing a larger hollow fuselage to neatly fit and properly ventilate all electronics. On the testing side, we learned that we need to start testing a lot earlier and calibrate the accelerometer before every flight to avoid control issues.
Gracias. ¿Preguntas?